All right, guys, I have a question from 7-2.
They give us a standard deviation, and it was like an explosive exponential graph or something. But we never learned about
Oh, is that the only? What else did I sign more from that little piece? You have I gave away. Oh.
I went to a tutor and they couldn't figure it out.
Oh.
So that's,
could they not just look it up in the section?
They did. They did.
So the exponential distribution was back in chapter 5. But I can take that out of there. So guys, hey, everybody, I'm gonna throw some homework out. You wanna hear? Guys. Yeah, there you go. Shut the hell up. Section 7-2. Number 47 to 54 deals with exponential distribution. So just throw those out. We didn't cover exponential distribution. I didn't have enough time. Yeah. That's why it's a good idea to email me, if you're having a lot of trouble. Or come see me.
I got stuck.
Yeah.
Yeah, 7.3. Well, it says 7.3.
Oh, yeah. All that matters is that it's 47 through 54 in chapter 7. Cool. That's what asking questions does for you. All right. Now maybe I'll get more questions because you're all like, maybe he's going to throw this one out too. That would be awesome if I could trick you into doing that. Yeah.
I don't remember, it was in like all of them for section 8.1. But it asked if you could.
Guys. Yeah.
It asked if you could, let me see if I can find it. Like for 97, letter C says what distribution should you use for this problem? And they said that you could use the normal distribution because you knew the standard deviation. What does that mean?
All right, so let's review. Why were t-scores invented?
For when we don't know the standard deviation?
Yeah. Well, no. Here. When you say the standard deviation, that's not quite right. There's two standard deviations that I could know. I could know the population standard deviation, or I could know the... Which one of those is going to be less accurate? Sample, because I don't have all the information. I'm taking a sample from a population. In fact, if I take a sample and you take a sample from the same population, we'll end up with two different standard deviations. So t-scores were invented to cover my ass for when I don't know sigma, when I don't know the true standard deviation of everybody, when I only have my estimate from my sample. So t-scores were invented for when sigma unknown, only S known. It also has to be normal, just like z-scores. So to use a z or a t, it's got to be normal. So either they got to tell you it's normal, or what? If they don't tell you it's normal, what else can make it normal?
30.
Yeah, if the sample size is over 30. All right, guys, you gotta work with me here. Turn off all the cell phones. I mean, I don't make a big deal of that because I shouldn't have to. Stop all the talking. Let's cut that shit out. If you have a question, it's fine. If you have a comment, it's fine. About statistics, it's great. But you gotta work with me. So this is why t-scores were invented. So when I don't know this, when I only have an estimate for this, I need t-scores. And the reason I love the idea of this is if there's something I'm not sure about, then my confidence interval has to get a little bigger. I have to catch more data to compensate for the fact that there's something I'm not sure about. So that's why these will always be bigger than a z-score would have been. You can see that on the chart we talked about last time. I like it. So what they were saying was, I don't have to use a student's t distribution because I know sigma. I know the population standard deviation. If I didn't know sigma, I would have to use a student's t distribution instead of a normal distribution.
Okay, so even if they tell you that the population is not normal, but you have the population standard deviation, you can still use...
Well, no, if they say the population's not normal, but I know sigma, that's still not enough information to tell me that I can use z-scores. What else do I have to know? Yeah, I have to know that n is more than 30.
Okay.
If n is not more than 30 and these two things are true, I can't do shit. At least not at stats 1 level.
Okay.
Stats 2, you could do some shit. Stats 1, we don't know. Alright, I like it. It's not our fault, it's just not covered in stats 1. I like it. Anything else from homework stuff? Like, are you guys doing it? Some of you guys are sort of doing it, but not really. You found solutions manuals somewhere. It feels nice to write the answers down and have them be right, but it's way too obvious. Make me work for it a little bit. Actually, better would be do the homework yourself. You know, it's better to make mistakes in the homework, and then you'll do so much better on the test. It's crazy. If you think the homework grade is going to cover you for bad test grades, you're not thinking correctly. This is so desperately not true. All right. You'd rather have a really bad homework grade because you did everything wrong and you didn't have time to make corrections, but you did it. And you're going to do better on the test than you would have otherwise. All right. I know a lot of you guys are doing your homework honestly. I love it. But way too many of you aren't. And you know who you are. And so do I. All right. Anything else from homework? Yes?
How do you calculate the error bound?
I like it. So, how many confidence interval formulas do we know so far? 3. We got this guy. Here's a nice little review of confidence intervals. We got this guy here. And then we got, the next thing we did was this guy here. And then the last thing we did here, the most recent thing we did was this. Now these can all be sitting on your formula sheet. I'm getting to your question, by the way. Do you see how this is so beautiful? I don't let you write notes because I want you to know the shit, not your notes. But why is this formula, which I allow you to write, a beautiful note? When do I use t-scores?
T-scores when you know this.
When you know S, when you don't know sigma. I mean, the formula tells you when. T-scores were invented for when you only know S. If I know sigma, and it's a normal distribution, then I can use z-scores. I love it. So, now coming to your question. Which parts of these are the errors? That's the error bound. They call it error bound because it's kind of like that's the boundary beyond which you're saying, I'm not going to consider that as part of this. So that's why they call it bound. But it's just the error. That's the error, and that's the error. So it just depends on which situation you're in. I like it. Cool. There are some problems that give you, like, confidence intervals that have already been made. I don't know, Jeff. You can do it? Sure. So there's a confidence interval that I made. Can somebody tell me what the mean must have been? Where would the mean be? What are these numbers? That's what I get after I do what? All right. After I add and subtract this, right, from the mean. So where must the mean be in any confidence interval? It must be right in the middle. It's got to be, because I added something to it and subtracted the same amount from it. So how do I find the mean if they give me the confidence interval already made? Average those. I love it. Does that make sense? The mean's got to be right in the middle. Why? Because I add something to it and I subtract the same amount from it. So it's got to be right in the middle. So there are a couple of problems in the homework in a few different sections where they ask you this kind of question. And at first it sounds like, how the hell am I going to know that? I don't know anything. So you take the average. So the mean is going to be the average of these two. So you get 18.2 divided by 2 is 9.1. And now what's the error bound? Because I had a feeling either it was they asked you to calculate it or they gave you this kind of problem. That's the two places I know that kind of question could happen. What is the error? going to be here? How do I calculate? How did I get 10.7? I took this and I added the freaking error. So how much did I add to 9.1 to get to 10.7? 1.6. And what's 9.1 minus 1.6? The other side, of course. So that's a question I can ask you outside of statistics. If I just phrase it differently, the math is really easy. What's the middle of this, and how far is the middle from the side? That's what they're really asking. So here the error would be 1.6. I like it. Cool. That's less a stats problem and more just a calculation problem. Yes?
Just to clarify, I'm not trying to be like nitpicky, but is it the X bar, the sample mean that we just did?
Yeah, X bar. Yeah, you're good. So that would be just the X bar. We're trying to estimate what the mu is. I like it. So anything else from homework stuff? We actually made it through all of Chapter 8. We're going to go back and finish that handout from last time and do a couple examples of T-score confidence intervals. And then us crazy people are going to get to the next chapter after that. So everybody's got that handout from last time, right? This T-score practice handout?
Do you have extras?
Yes, somewhere. Here. So if you didn't get that, you probably didn't get this either, right? Thank you. Sure. What's up? Oh, okay. All right, cool. Oh. All right. So I think we did the first few in that one. We had to finish off the bottom part of it. So speaking for those of you who missed last time, you missed kind of a rough class to miss everyone. So we got to the point where we identified, let's recapture why we're allowed to use the z-scores here on this first one. What two things do I need? What thing do I need just to do anything? It's got to be normal. So this one is nice. It's normal. They just tell me it's normal. So how big does the sample have to be? It can be any size it wants to because they already told me it's normal. Right? So if the population starts off abnormal, right, some freaky looking thing, then you have to have at least 30 to guarantee that the sample means look normal. But if it starts off normal, you're golden. You can take 1 and it's normal. So 2 is going to even make it more normal. So it's already normal, so that's good. And then what is it that, so I need it to be a normal distribution to do anything. Now what distinguishes between Z and T? The kind of standard deviation that I know. Not just do I know a standard deviation, but do I know the right one? Do I know the real, full standard deviation? Well, which standard deviation do I know? Population. That's why I'm allowed to use z-scores. Z goes with sigma. T goes with S. And what was S again? Sample standard deviation. I love it. Let that make sense? If I only know S, that's an approximation for sigma. I took a sample, and the information I find from that sample is almost guaranteed to be wrong. It's not going to be the same as for everybody in the population, but it's my best guess. So that is, S would be a guess, like here. So I need a bigger score to kind of cover me for the fact that that's just a guess. So that's why the t-scores are always bigger than the z-scores. Why was I allowed to use a t-score here, or why must I? First off, it says the population is not normal, but
And it's over 30.
yeah, the sample size is bigger than 30. So that guarantees my means will come out normally distributed. I know S, and that's why I have to use T. Kick ass. We're going to go back and figure out these scores, by the way. Why is C a big fat no? Yeah, I know sigma, but, oh, well, too bad. It's not normal. Right? It's like having gas in your car, but no engine. Sorry, that would be a rough morning to wake up to. And then here, this one, it's normal and the sample's big. That's great. Why do I have to use a t-score? Yeah, because I only know S. I don't know sigma. Kick ass. So let's go back. We didn't do this last time. If you didn't do this yet, try to figure out. Everybody should be able to do the first one. Some of us might need help on the second one. So try to find out what the z-score would be here. So I tell you, it's a 90% confidence level. That's the main thing to realize. I have a couple of extra z-score charts if you need one. Just reminding us, is 90%, it's on this little baby chart here, right? That kicks ass, so the confidence level is 90. So my critical value, my z-score is 1.645. Now, kind of a dumb question. Confidence interval got to go up and down. Where does that come into play, that up and down part of it? It's kind of a dumb question, but I mean, that's one z-score. It's 1.645. So where does the up and down come in? Yeah, it's in the formula, right? So depending on the way you look up your z-score, don't put a negative down there. It's the plus or minus is built into the equation. Because you're going to go up so much and down so much. I like that. Now here, this is the one we know I need some help. Those of you who were here, before I look up my t-score, what do I have to figure out? How do I use that chart correctly? Yeah, degrees of freedom. So degrees of freedom here are going to be 38. So if I look at my t-chart, now those of you who weren't here last time, you can get through the whole denial of yes, a whole other chart. Up here, don't worry too much about this one, but if you do this one, it's all right. What's my confidence level for this? 98%. So how much is going to be outside of that in the two tails? 2%, 0.02. So I've got 0.02 in two tails, and then I go down until I hit the degrees of freedom. 38. Whoa. There, 2.429. So this row directly correlates to confidence intervals. So I'm 98%, I'm going to go there. That's the 2% that's outside. 99 is there. 95 is there, so forth. Today we're going to get into something called hypothesis tests, where you could have one tail. I want to have a claim that I'm paying more taxes than somebody else, so I'm only going to be interested in going in the upper tail. So this will be a one-tail test. We'll find out later today. So this came out to be 2.429. Kick ass. This was a no? Great. Done. We can't do anything. It's not on a test, dear God. If you think you can't do anything, still do it. I just can't. I won't put a problem that I'm like, if you don't notice you don't have to do it, you're going to spend a lot of time. I'm not going to do that. I'm not that evil. Some of you guys think I'm evil. I'm not that evil. Give me a few more years. So part D, we already identified I need to use a t-score. So take a minute. If you haven't looked this up yet, try to find the correct t-score. Got to get your degrees of freedom so you can use this chart. where am I looking at here?
Point oh one.
Yeah, where?
Point oh one.
0.01. I like it. 99%, so there's going to be 1% outside. And then I'm going to go down. What's my degrees of freedom? 60. So I go all the way down to 60. 2.660. I don't know if you guys have noticed. So that's 2.660. I don't know if you guys have noticed. Do these numbers at the very bottom look at all familiar? 1.6 for 5, 1.96. 2.326 is 2.33. That's for 98%. We used 2.575 before for 99% because we estimated it to be between two things on the z-score chart. This is just a little more correct, 2.576. So these down here, where it says large, these are actually z-scores. Do you guys understand? Because when my sample is smaller and smaller and smaller, how do I feel about the standard deviation that I find from my sample? Do I feel more or less confident as my sample gets smaller and smaller? Less confident. So therefore my t-score has to be even more and more bigger than the z-score would have been. So if I reverse that, in the limit that my sample gets really big, gets large, and I know that's a very fluid word, but oh well, too bad for us. It's got to be vague. Then I don't need a t-score anymore. I could use a z-score. When my sample gets really big, the S is essentially equal to sigma. You guys with me? So if my population was 3 million and my sample size is 2.8 million, my freaking S is equal to sigma. That's all there is to it. So big. I'm really, really certain about what I'm looking at. Maybe. I'm going to come back to that, because now I can use my t-score chart. This always freaks people out when I do this. I can use my t-score chart to look up z-scores if I just go all the way to the bottom. So if I go all the way to the bottom, I find a z-score. If I stop, I find a t-score. That's the difference. Yeah, maybe. So let's try a few problems out. It's always a little bit easier once you actually see something happening. We'll leave you in darkness back there. There you are. All right, guys, let's try a couple together here real quick. Let's say I take a sample of 41 students. Find an average. Let's see, average height of, let's say 61.9 inches. And S equal to, say 3.7 inches. Okay. So we take a sample, we find a sample mean, sample standard deviation. Now problems very often will not use the letter S. They'll say, I took a sample of 80 and I find a mean of 20 and a standard deviation of 11. Well, that standard deviation is the sample standard deviation. Why is it important to know which standard deviation it is? So I know if you want to use T or Z. I like it. So here I'm being very nice and just saying S, which is giving it away. So first off, why am I allowed to do anything? Yeah. N is 41, which is bigger than 30. Check. So I can do something. So now let's create a 98% confidence interval for the true mean height. So which formula am I going to use? anytime I ask for a confidence interval, I hate teaching like this, but I've made you go through all the derivation of where things came from. So now I can just say, if I ask for confidence interval, find the formulas that have plus or minus in them. That's the whole idea of a confidence interval, right? So that kind of gives it away. If the problem didn't say make a confidence interval, don't use those formulas. I have to say this so often nowadays. I didn't ask for a confidence interval. I didn't ask for a confidence interval. People making confidence interval everywhere. So which formula do I want to use? Definitely not the one with p's in it. Yeah, x bar. Good. T.
Divided by
TKS. So I got to use a t-score because I only know s. I'm allowed to do something because of this. Let me stop there for a second. How are we doing? Because my options were this, or z sigma, or p hat. There's no percentages here, no proportion, so I don't want to use p hat stuff. So what do I need to figure out? What do they tell me? What do I not have here already? I know s. I know x bar. I know n and et. So what's to get the t-score? What's my degrees of freedom going to be? 40. So, and what am I going to look at? Which column am I going to look at for the 98%? Probably the one with the 2 up there, right? I like it. So you go all the way down until you hit 40. So I get 2.423. So if you've done the confidence interval homework using z-scores, this should be easy. I'm just using a different chart that actually is easier to read, to be honest. So I get x bar, give or take, what was it? 2.423 times 3.7 divided by the square root of 41. I like it. So 2 mistakes people make. That is s. Don't divide by square root of n and then put it in and divide by square root of n again. Don't divide by square root of n twice. You only have to put the s in there. You don't have to divide it yourself. It's built into the formula. Secondly, people put 40 there because they know this. That's got to be n. N is 41. So now, just like before, my suggestion was do this first. Figure out what the error is first. So I get basically 1.4, right? 00. So it'd be 61.9 plus or minus 1.4. And I just have to add it to that, subtract it from that. It's really kind of nice. Yeah, 60.5. Okay, I like it. How are we doing so far? I mean, that's... Again, I hate teaching plug and chug, but I didn't teach it that way. I'm forced to go through all the where things come from. Now it's plug and chug. Now you can look back, you can pick the right formula, you can say, what is it that I don't know? You can find what you don't know. Plug and chug. Then once you get the numbers, now you got to step back and say, crap, I got to write that paragraph for him, or that sentence. So take a minute and try to write the conclusion for this. No. Where's the t-score up here? What are these? These were heights of students, right? These are inches. I like it. What units do z-scores have? None. So the only units come from this, which is inches. So it's so many inches, give or take so many inches. So I'm going to say that, well, it should be captured in your statement, right? How does your statement start off? I like it. We are 98% confident at the interval 60.5, 63.3 inches contains the true mean height of students, blah, blah, blah. I like it. Please, how many intervals are up here? How many intervals are up here? How many intervals are up there? One. One interval has two endpoints, yes. But don't make this plural. There's only one interval. An interval is from something to something. So I only have one of them sitting around up here. Sorry, this is a little pet peeve. Don't put intervals. You only have one interval. I like it. You're all like, picky. Yeah, I'm a math guy. What do you want? All right, cool. I like it. So that should feel unbelievably much like the ones we were doing before. It totally is. It's still just a confidence interval. I'm just using a more conservative number here to cover me for this unknown piece here. I like it. All right, let me put one up here and let you guys do it all by yourselves so I can shut up a little bit. Don't get too excited. We'll start talking again later. Has everybody got what they want from this here?